A popular strategy for setting asymmetric centers is the use of chiral auxiliaries. Shown on the note card on this slide is an example of Evans' chiral auxiliary, an oxazolidinone with, in this case, an angular isopropyl group shown on the wedge. In this video, we will talk briefly about both the base and how it forms an enolate, as well as trajectory of the incoming electrophile that sets the observed final stereochemistry of the product. To begin, we need to look at formation of the enolate. The enolate is formed by using the base lithium diisopropylamide, or LDA. In this case, we have two possible protons, which I will draw in. We have the one on the wedge and we have the one on the dash. You'll notice that the chain is in sort of its extended conformation, not curling under, and that's due to the steric repulsion of the isopropyl group on the chiral auxiliary. The chiral auxiliary also protects the proton on the wedge such that the LDA base must come in from behind the molecule to abstract the proton on the dash. That then gives us the enolate shown here, which is our Z enolate. That means that the higher priority oxygen group and the continuing alkyl chain are on the same side of the alkene. Now that we've identified the appropriate enolate geometry, we now need to think about what this looks like in terms of its three-dimensional projection in space. On the lower left part of the slide, I've redrawn the enolate by tipping it back. You'll notice that the isopropyl group is now pointing up, and I've also drawn in the proton also on the same carbon possessing the isopropyl group. We will now use this drawing of the enolate to evaluate the two different trajectories, that is, the two different approaches that the incoming electrophile can follow as it moves toward the enolate nucleophile. These enolate approaches are shown in the middle of the slide, where on the top we have the benzyl bromide coming in from the top face, that is approaching from the top of the slide. And on the bottom, I've got the benzyl bromide coming in from the bottom face, or the bottom of the slide. You'll note that the benzyl bromide, when it approaches from the top, runs into steric interactions with the isopropyl group. These steric interactions are substantially less when we compare the size and bulk of the isopropyl group to the proton that I've circled. This leads us to predict that the most likely path or approach that the incoming electrophile can make is from the bottom face. Once we then draw the new bonds that have formed from the two different electrophile approach trajectories, you'll see that we end up with both possible diastereomeric products, the benzyl on a wedge and the benzyl on a dash. The dashed benzyl matches both the lower energy pathway, that is the less sterically inhibited electrophile approach, as well as the observed stereoselectivity in the product shown in the note card in the upper left.